Hello guys, today we're going to be doing a simulation with three different types of flow going over a cylinder. We're going to be doing a laminar flow or an inviscid flow and two types of viscous flows, both laminar and turbulent. And we're going to start by making our geometry by sketching a circle here. We can make the diameter for that 1 meter. Since we're working with SI units. And then we're going to make a square going around of 50 by 50 meters. This here is going to be 25 meters. This will be 25 meters as well. And this one, excuse me, 25. And then this last little bit, 25. And once we have that, we can make our rectangle from this end all the way to that end. And then we can trim these pieces that we won't need anymore. And then go ahead and create a surface from this sketch that we just made. And generate it. And we should have, our geometry here. And we can go ahead and leave and start our meshing process, which will be a little different from what we've done in the past. We're going to use an inflation tool and a tetrahedral type of mesh around the whole geometry. So once this mesh loads up, we can go ahead and change to our XY plane. And we can insert a method mesh of this geometry. We're going to make it triangles, and that should be fine. Go ahead and generate that. And we can see here, it looks more fine towards the cylinder, which is what we want. But we're going to actually insert another sizing mesh here around this cylinder, and we're going to apply that. And let's switch our units here. We're going to make this number of divisions. We can make it pretty fine here. We can make it 200, make sure it doesn't capture any curvature, and give it a hard behavior. And generate that. And then now we can see that this has become a lot more fine towards the center, towards the cylinder. And we're actually going to make one more mesh here, which is going to be our inflation. Oops. We're going to select that for the geometry. Oops, sorry. This is going to be actually the face. And the boundary here is going to be the cylinder itself. The inflation option, we're going to make first layer thickness. The first layer height can be pretty small. Growth rate's good. And the maximum layers we can make about 100. We can see how this looks once it's done. Yeah, it looks pretty good, especially towards the center, which is exactly what we want. And now we can, since this out here looks pretty coarse, so we can go ahead and change to the mesh size from 3 meters to, let's do 0.12 meters. Let's see how that looks. We want it to be very fine so we can get all the velocities and contours looking good. And once this finishes meshing, we can move on to the setup for each of our types of flow. Okay, so now you can see it's clearly a very fine mesh here. And we gotta make sure that we don't have too many elements down here. And 340,000, that's fine. As long as we're below the 500,000 threshold, we should be good. So now that this is done, we can actually make our inlet here. Create a name selection. We can make our outlet and our symmetry planes. And of course, our cylinder itself. And now that this is done, we can see all our name selections here. We can go ahead and go to the setup, and the mesh is going to remain the same for all the flows. So the next two flows that I'm going to do, which are the laminar and the turbulent flows, will not have the geometry and the meshing aspect of it, so I can just fix that while I'll just finish the setup for those, since, like I just said, the meshes, the geometries are going to be the exact same. So now we're just trying to update the mesh here. Now that that's done, we can move on to our setup. Make sure that's set to double precision. And we're going to be doing different types of methods here, and models, of course. For the Inviscid flow, we're going to make sure that we have a simple method, which should make it converge faster in theory. So in this model, we're going to make sure that we have it set to Inviscid flow. Hit OK there. Everything else in here should be good. The materials, the air, can change this to 1 kilogram per meter cube. Everything else is fine. There's no viscosity because it's Inviscid. This is fine. Boundary conditions, we're going to make this inlet 5 meters per second as per the instructions state. And our outlet, we got to make sure that we have to prevent reverse flow. So once that's applied, we're going to check our reference values here, and we're going to be computing this from the inlet. Our area should remain 1 because the depth is 1, and depth times our diameter of 1, it's still just 1. Our velocity is good. And we can go to our methods, which is what I was talking about earlier. We can make this simple and change this pressure for the Presto pressure. Under controls, I don't believe we have to change anything. Nope, nothing here. Oh, there we go, the residual. We're gonna keep it at this for speed purposes, but I'm gonna make sure that our convergence criteria is a lot smaller for our report and everything else that we do. So that's gonna be done. I'm gonna change those values. But for speed purposes of this calculation, I'm gonna keep it as that. We can maintain a hybrid initialization and initialize with 10 iterations. And now that that's done, we can go ahead and run our calculation. We can just do 200 iterations for now, just to make sure that it's a fast process. But same as the convergence criteria, I'm going to make sure that there's more iterations being done to make sure that it converges fully. And I'm not sure how this will take, so I might cut this part out until the calculation is done running. So now that our calculation is complete, we can go ahead and pull the things that we want out from them. So we can first look at the pressure, the static pressure contour, which looks good, symmetric as it should be. We can also look at our velocity contour, which again is the same, should have the highest velocity, which is 2 times the input velocity, which is about 10, which is right, and the lowest velocity at the stagnation point in front of the cylinder, which is where the inlet velocity is coming into. Now we can check our plots, our pressure coefficient plot on the cylinder, and it looks perfect. It goes from 1 all the way down to -3 and then back up to 1 on every position of the cylinder, you can see here. And then our velocity function on the cylinder should look, just like that. Again, it's 10 here at the highest point, which is right in the middle of the cylinder, and then it's 0 at the stagnation point and the other stagnation point right behind the cylinder. So that all looks good. And then for our report, we can look at the forces here on the cylinder. Go ahead and print those out. And we can see a total coefficient of drag of 2.896 times 10 to the -4th, which is very small and very good because, again, Inviscid flow should be very small and close to 0. So now that that's done, we can go ahead and check our streamline in our results. So we can go back to our workbench here and open our results. And once this opens, we can check our streamline on the XY plane once again. Add a streamline, 3D, all domains. We can start from the inlet. This vertex sampling, we can make, say, 100 points and go ahead and apply that. And you can see very well these streamlines, which are pretty symmetric here around our cylinder. So that should be everything for this Inviscid flow, and now we're going to be moving on to our laminar and turbulent viscous flows. Thank you.